Now I want to use this idea of df by dz bar to go back to Cauchy's theorem because it gives us a wonderful, more powerful extension of Cauchy's theorem so far. There's much more to say about the subject. And I just want to remind you, I kind of summarize some of the stuff from previous videos. We did a microscopic closed contour. So CH was a little closed curve, a little square of side length h. And I took the limit of the closed curve integral per unit area, so dividing by h squared. And there was a bunch of limits and stuff like that, but it turned out to be something that could be expressible in terms of partial derivatives of f. And specifically, if we factored out an I, it was I times df dx plus I df dy. The main punchline of that was that that's 0 if it's complex differentiable, if basically the Cauchy-Riemann equations are satisfied. But we now have this new notation that that's just twice df by dz bar. And so this is a very succinct way to say, here's what measures that microscopic closed curve integral. Now I want to go back to the proof of a non-microscopic integral, an integral around the boundary of region D. So I have for some region D, we've got the boundary of that region D, and this is exactly like the proof I have on video. It's somewhere for Green's theorem. I'm going to put that on a grid. I'm going to slice it up into a grid, and let's say I is an index that measures just labels them this way, and J measures them this way. And so this rectangle, for example, will be rectangle Rij, and its boundary, these four segments, would be the boundary of Rij. Okay? The claim is that the integral around the entire boundary is the sum over all i's and j's, all these rectangles, of the integrals over the interior boundaries, all the boundaries of these guys. The reason for that, this is what makes all these theorems work, is that if I look at any two adjacent rectangles, I'm going to be picking up the segment that's between them twice. One's going one way, one's going the other. And there are all the interior boundaries will cancel out, and I'll just get the stuff around the edge. Now, to be rigorous about this, you have to be careful about how like a stair-steppy thing is actually limiting to a curve. And there are some subtleties there, but they really do work out. Okay? Well, so now I'm going to take the limit as these get microscopic. Okay? So I'm just going to make these arbitrarily small. And so this is going to be the limit as h goes to 0. Let's say this is the size of the thing. Okay? And then I'm going to just put in a factor of 1 over area and area. Okay, 1 over h squared times h squared times the sum. And then I'm going to convert this. Well, first I'm going to just leave it. Once I get the limit going, I can convert it. Okay. F of z dz. Okay, so the limit of 1 over h squared, there's an ij there, of these integrals, that's the microscopic closed contour. What's left is the sum over all of them of the size of each rectangle times this guy. And of course, those df dz bars are evaluated at all the little points in these rectangles. Well, this is just going to become, and there's still a limit, h goes to 0. The limit of a sum of little bits of area times a function, that's just the integral over the entire region, which we are calling D, of 2i df dz bar dA. So in the first case I was doing, we didn't have to do any of that stuff because it collapsed. This was 0. But now what we've got, I'll summarize, is that we've got a measurement of exactly what's going to cause a closed curve complex contour integral to be non-zero. It says the integral over the boundary of a region of the function is going to be 2i times the integral over the inside of this funky derivative. And of course the corollary is if that's 0, then you're just going to get 0. That was the basic case of Cauchy's theorem. So this lets you go beyond just complex differentiable functions and lets you put in things like with z bars and things like that and get a lot of cool results about those. Okay, so let's look at just a couple things we can do with that. Let's look at, I want to go back to 1 over z. This is such an important function. And again, I want to keep making these analogies to the vortex vector field. Remember, that's v equals minus yi plus xj over x squared plus y squared. That's this vector field that has no curliness anywhere but at the origin. These arrows, even though they're turning around, are set up so that they don't turn a pinwheel anywhere, except right at the origin there's kind of an infinitely concentrated bit of curliness. I want to make that a little more precise without being incredibly rigorous. Okay, so let's look at, if I look at any region, any simple region, including the origin, in other words, whose boundary, so here's D, and here's C, which is the boundary of D, any curve enclosing the origin just once, and then so that's this nice region that actually contains the origin. We know that this guy, we calculated this already, it was 2 pi I. And that's this whole thing about winding number and index and things like that. Okay. Now, if 1 over z were actually didn't have a singularity, if it were a nice function at the origin, what would this tell us? Okay. We could use this and then just say, okay, this is 2 pi I. Okay, if that's 2 pi I, then I can cancel the 2 and the I. Okay. And so I would say that df, the integral over that whole interior, df dz bar, would equal pi. That's interesting. Well, of course, df dz bar, this doesn't seem to make sense that I would integrate over the region, but let's run with it for a minute, okay? And in particular, it's a really weird statement because it says it doesn't matter what d is. If this were a function, there's a dA I'm missing here. If this were a function, it would have the very strange property that its integral over any region containing the origin, no matter how big or small, was always the same number, pi. I hope I'm not missing factors of I or 2 here, but I think I'm getting them right. If I'm not, don't sue me. It's just a YouTube video. Okay. But it should be right. So this is a weird fact, that we've got something that probably doesn't deserve to be a nice function, and it has a property that nice functions would never have, is that its integral is highly insensitive to exactly what region you integrate it over. Okay. Well, this is where it'd be nice to have a little bit of familiarity. This is what the delta function does. The delta function is basically something like in one dimension whose integral, or whose graph kind of looks like nothing, 0, 0, 0, 0, then an infinitely concentrated spike, and then 0. And its the property is the integral of this delta function from a to b, or one property is that it's equal to 1 if 0 is properly in here and 0 otherwise. Okay. A better way to do it is to say that the integral over all of r of delta x times any other function is exactly just what that function is at 0. And this is a special case if the function is just a step function that's 1 from a to b and 0 elsewhere. Okay. Turns out that this is the defining property of the delta function. It's not really a function, but it's an enormously useful object. It's called a distribution, although the existence of the delta function predates the idea of a distribution by quite some bit. Basically, it's an infinitely concentrated spike that it makes sense to integrate but not evaluate. So it makes sense inside an integral but doesn't really make sense anywhere else. Well, look at what's happening down here. I've got this something, some gadget, that it's sort of like a function, and it has exactly the two-dimensional analog of this property, except times pi. It's pi if this region includes the origin, but if d is over here, and its boundary is here, then this function is perfectly nice, and Cauchy's theorem in the usual sense applies to show that that closed curve integral is 0. So in fact, the punchline is that, in a sense, 1 over z, its derivative by dz bar, is just pi times the delta function. I think that's really cool. And in fact, it's the start of a very sophisticated story. It's very useful. Okay. And again, I have this feeling I'm missing a 2 or an I somewhere, but I'm not going to worry about it, to be honest. So maybe I'll do an annotation. All right. So this is nice because it says that, as we expect, 1 over z, remember, this is a function that's algebraically built just out of z. So everywhere except where it's singular, this d by dz bar should be 0. And that's kind of the property that delta has. You want to think of it, to some extent, as evaluating to 0 everywhere except right at the origin. Okay, so this is the 2d delta in the complex plane. But it's at the origin, 1 over z is doing something pretty weird, but not undescribably weird. It's exactly having the property that it's d by dz bar derivative, which detects any problem with Cauchy's theorem, anything interesting going on in Cauchy's theorem. It's about the simplest thing it could be. It's just pi times the delta function. Okay, this is exactly like what goes on with the vortex vector field. If I look at the vortex vector field, if I look at a similar region and I look at the ordinary vector line integral of the vortex vector field, and I take some region, including the origin, simple region, nice simple closed curve as its boundary, then this is 2 pi. And Green's theorem tells me that this should be the integral of the scalar curl of that guy, dA. Well, that's a little suspicious, of course, in the same way that scalar curl shouldn't exist if this vector field is blowing up right at the origin. And it's also weird that this doesn't depend on d. But the way to explain that is, again, to use the delta function. It says that a nice interpretation of this is that the scalar curl of the vortex vector field is just 2 pi times that delta function supported at the origin. Pretty neat. Okay, so a tiny little intersection of complex analysis and the basic parts of the theory of distributions, and in particular delta functions.